Okay, good afternoon all of you. Once again, today's class is on differential equation and the topic is class of first order nonlinear ODEs. Actually, we was learning about first order differential equation but of higher degree. So this is the continuation of that class. So today I shall be talking about specially on Clairaut's form and the transformation of equations into the Clairaut's form. How will you transform the equations in the Clairaut's form, right? That is the main target. Actually, you see, you have already known about that. The differential equation of the form y equal to px plus function of p. This is the Clairaut's equation where p is the first order derivative dy dx, and you know that its complete primitive is y equal to cx plus f of c. And how will you get this? Because if you differentiate both sides with respect to x, once again, if I show you, let me show you once again. So your equation is y equal to px plus function of p. P is your dy dx. So if you differentiate this with respect to x, then dy dx equal to p plus x dp dx plus f dash p dp dx, because you are differentiating with respect to x, right? Now this is also your p, so this will cancel with this p, so you are remain with your remaining equation will be after calculation x plus f dash p into dp dx equal to 0, right? Okay, so either you have dp dx equal to 0 or x equal to minus f dash p, right? dp dx equal to 0 or x equal to minus f dash. So dp dx equal to 0 implies p equal to constant, that is some c. So if you substitute your p equal to c here, you will get y equal to cx plus function of c. So that is the complete primitive or general solution of the equation. And what about x plus f dash p? You have another relation, x equal to minus f dash p. So let it this be 3. Let this be 3. Equation 3. This is your 2. P equal to c, and the given equation, that is this equation, is known as 1, equation number 1. So if you substitute your x equal to minus f dash p in the given equation 1, you will have y equal to minus p f dash p, right? Because your x plus function of p. Okay, so this is your 4. So from 3 and 4 you will get a solution if you eliminate p. If you eliminate p, this gives you another solution which doesn't contain any arbitrary constant or p. This type of solutions are called singular solutions. This type of solutions are called singular solution of the equation. So you see, Clairaut's equation are observed to contain two sets of solution. That is the general solution involving only arbitrary constant only. This is the general solution of the integration, and the singular solution involving no arbitrary constants and of integration. Okay, if you are interested to find the singular solution, then we have to solve 3 and 4. 3 and 4 try to eliminate p, then you will get a relationship between x and y, and that will give you the singular solution. Okay, now there is a question about this. So before I move to the geometrical interpretation, let me tell you one thing. The differential equation of the first order but not of the first degree may or may not possess a singular solutions. Number 1. So as a natural curiosity, we should be interested to know whether there exists some criterion to examine if an ODE of aforesaid type admits of singular solution or not. That is the question. One clue in this respect has been the Clairaut's equation, right? Clairaut's equation. This is your Clairaut's equation. I was talking about this Clairaut's equation. So thus if we manage for which existence of singular solution is guaranteed, that means one clue in this respect has been the Clairaut's equation for which existence of singular solution is guaranteed. So thus if we manage to transform a given first order ODE to Clairaut's form, if we can manage to transform the given ODE to the Clairaut's form, then it should have a singular solution. It should have a singular solution. So if any equation can be transformed to first order ODE of higher degree can be transformed to a Clairaut's form, it must have a singular solution. That is guaranteed. Contrapositively, we may infer that if one ODE admits of no singular solution, there will be several ODEs where there are no singular solution. It can never be transformed to Clairaut's equation. It can never be transformed to Clairaut's equation. Okay, clear everybody? So however, we cannot tell that if any first order ODE admits of a singular solution, it is always transformable into Clairaut's form. The other unfortunate incident that really troubles us is the absence of definite transformation rules. Actually, there is no definite rules for getting into the Clairaut's form. So that is very unfortunate for us. From where we can get that it is known that this can be done for a particular problem. So all that we have in our hand is the empirical transformation rules that I will discuss later on. So before going into the detail, let's have the geometrical interpretation. So geometrically it represents the family of straight lines in the xy plane. So look at the general solution, y equal to cx plus f of c. It represents the family of straight line in the xy plane. If this family has an envelope, it is found by differentiating with respect to c. Then we have x plus f dash c equal to 0. That is already we have this relation. Here you have x plus f dash p. It is similar to that. If you differentiate with respect to c, you will get this. So by elimination of c between these two, that means I was talking about this and this. It's the same thing. The elimination of p between this equation and this equation. So both will give you the singular solution. Both will give you the singular solution as already explained in here in the calculation. So therefore the curve represented by the above line is the envelope of the family of lines. Is the envelope of the family of lines y equal to cx plus fc. And you know the singular solution of the Clairaut's equation becomes the envelope of the family of lines. So what is the singular solution represents? It represents the envelope of the family of lines of the given general solution. And you know that this is the definition of envelope. The curve given by the singular solution touches every member of the family of lines given by the general solution, and also at each point of the curve it is touched by some member of that family of lines. Okay, so that was the concept of envelope. It is already known to you. And what is the geometrical interpretation or observation? The singular solution of the Clairaut's equation becomes the envelope of the family of lines. Family of lines, that is the general solution, complete primitive of the Clairaut's form. That was the observation. Also we can observe more. So far we have been taking the Clairaut's equation in the form of y equal to px plus f of p, with the underlying assumption that x is independent and y is dependent variable. If p were not 0, then dy dx can be written as 1 by dy dx. So writing q equal to 1 by p, we have reformulated the equation. What is the reformulation? X equal to qy, q into f of function of y q. So 1 by q. So if you write this equation as g of q, so this is equal to x equal to qy plus, if you write this whole taking the negative also, so this equation can be written as x equal to qy plus function of q. Sorry, this is written p, this should be key here, q here. So this is function of q, right? So this is again in the Clairaut's equation, which is again a Clairaut's equation. So what we conclude that in this case, Clairaut's form is invariant under the interchange of roles of the two variables x and y involved. So you have only two variables involved. One is an independent variable, another one is a dependent variable. So we conclude that Clairaut's form is invariant under the interchange of roles of two variables x and y involved. That is already explained here. This is one of the most important observation. Next, we'll talk about from elementary results of calculus. One observes that very assumption of non-vanishing p OD is guaranteed that if y were a function of x, then x could also be expressed as a function of y. So that is why it is invariant, right? Let's now address the question of possible reduction of an ODE of first order but not of first degree to Clairaut's form. So there are questions people will ask about what is the rule, or is there any rule of transformation different for transforming different first order higher degree differential equation to Clairaut's form? As stated earlier, there is no specific general rule for that purpose. There are few empirical rules to be applicable to certain ODEs. For certain ODEs we can use some rule, but empirical rules, but there is no certain transformation rule, general transformation rule. So it is not valid for all the equation, it is valid for some few equations. So that is why there are some rules for you. This is your rule A. If the ODE appears in the form, if you can transform the ODE in this form, that was people was asking for so many years, that what is the rule. So there are some rules, but that is not general rule, it's an empirical rule for few ODEs. F being differentiable functions of, look at that, it's a py by x into x, y square equal to py by x into x, and function of py by x. P is your dy dx, actually p is your dy dx, first order derivative, right? So this is the thing. F being a differentiable function of its argument, then the substitution x square equal to u comma y square equal to v reduces to it to Clairaut's form, and the form will be v equal to u plus function of q. Form will be v is equal to u plus function of q, where q is dv du. Okay, so this is the thing, this is the rule A. Now there is another rule, rule B. If the ODE appears in the form e to the power by into bp minus a, where p is again your dy dx, p represents dy dx, and function of eby by p into eby by e to the power x equal to 0, a being a differentiable function of its argument, then the substitution e to the power ax equal to u and e to the power by equal to v reduces to the Clairaut's form. This is the Clairaut's form, where q is equivalent to dv du, right? Q is equivalent to dv du. In this case, p is equivalent to dy dx. Here also p is equivalent to dy dx. Let's have some examples for that. So first question is, I will solve some problems in this lecture so that you can understand how to give the transformation. Reduce the following ODE to Clairaut's form by using the substitution y u equal to x square and v equal to y square. So not always this substitution is given in the problem. So there will be sometimes it will be mentioned in the problems, but there will be so many problems where it is not mentioned, right? So and the equation is given by px minus y into py plus x equal to h square p. So let's solve. Look at the equation px minus y. Let me write the equation once again. Px minus y into py plus x. So how to transform into the Clairaut's form, and your substitution is given here. So this is the differential equation ODE, first order but not of higher degree. P is given by dy dx. Write P, and your substitution is given here, u equal to x square. So that implies du equal to 2x dx, okay, and v equal to y square. So that here is dv equal to 2y dy, okay. Now q is equivalent to dv du, right? This is dv du, and that will be given by, if you write dv equal to 2y dy and 2x dy, so y dy by x, y by x dy dx, right? And this is your yp by x. Look at that, you have a form of yp by x. So this equation can be transformed into this Clairaut's one. Look at that, it belongs to rule A. Look at that, yp by x is the function here, it is used as a function here. So you have yp by x, right? Now your equation can be written as, your given equation can be written as, the given equation can be written as p square, if you expand, p square minus 1 into xy equal to h square minus, h is a constant, h square, look at that, you have a h here, so if you multiply you will get this type of relations, plus y square into p, okay. Now what is your p? Okay, q is written as this. Let me write the equation first. Let me divide by p, you will get p minus 1 by p, dividing both sides by p. P is not equal to 0, obviously p is not equal to 0. Derivative, first order derivative is non-zero, so you have to mention here that p is not equal to 0, and you can write this equation pxy minus xy by p, left hand side, and right hand side will be h square minus x square plus y square, right? And you have to write in this form yp by x. Look at the form yp by x, right? Let me write, this is in the form of yp by x. So if you write in the form of yp by x, so you need an additional x here, so it is x square minus, if you write this is yp by x, so in the denominator you can write py into y square. Got it, right? So look at that, you have yp by x, you have yp by x, so it will easier for you to transform the equation in terms of q. So let me now transform the equation. This will be q, so q and x square is u, this will be 1 by q, so this is your v by q equal to h square minus h square, y square is v minus u, right? So look at that, all the terms have been transformed into q, u and v. In terms of q, there is no x, y and p, so now your equation will be function of q, v and u, right? So let me more simplify. If you do the simplification, you will get v into q plus 1, if you take, and u q into q plus 1, if you do the manipulation over there, h square into q and if you divide by q plus 1, you will have v equal to uq minus a square q by q plus 1, provided that q is not equal to minus 1. Okay, so look at that. This is your Clairaut's form. Right? This, the final result, final line is your Clairaut's form. V is equal to uq minus a square q by q plus 1, q not equal to minus 1. So this is the Clairaut's equation in u, v and q. Okay, because u is your x square, v is your y square. So what is the general solution in this case? General solution is v equal to cu minus h square c by c plus 1. This is the complete primitive, and you can substitute your u and v in terms of x and y. You will get the general complete primitive. Okay, so this is the directly you can get, and you can search for the singular solution also this problem, because you know how to calculate. You have to differentiate with respect to q. Now the question is, what happened if q equal to minus 1? What happened if q equal to minus 1? You look at that. If q equal to minus 1, then what is your q? Your q is yp by x. So your yp by x equal to minus 1. So yp plus x equal to 0. And so h square would be 0. In that case, your h square would be 0. So this will be 0. H square would be 0, which is absurd. Because h square is a non-zero quantity, right? So this is the case where q equal to not equal. What will happen if q equal to minus 1? You can further check that. So that was the problem, and that was how you will transform the equation, this given equation ODE of first order and but of higher degree to Clairaut's form with this substitution. Let's have another equation. Another problem. Let me check another problem. The problem number 2. The transform the following ODE to Clairaut's form by means of the suitable transformation, and hence solve it. So you have xy into p square minus x square plus y square minus 1 into p plus xy equal to 0. Let me solve this equation, but you see there is no transformation rule is given to this problem. So you can check rule 1 here. You can check rule here, rule A. That is the first rule. You can empirical rule. You can check here. Let me substitute here. That let me substitute x square equal to u and y square equal to v. You can try this for. Okay, let me substitute. Then the given differential equation. So let me solve this equation. So you have xy, let me write again once again the equation. Xy p square minus x square plus y square minus 1 into p plus xy equal to 0. Okay, this is the equation. Now x square is equal to u and y square equal to v. Okay, so now 2x dx equal to du and 2y dy equal to dv. Once again, as the previous case. So you can write that equation. Again, you can write q equal to, you have q just already calculated in the previous problem, yp by x, right? This is your q is this, and q equivalent to du dv du, q equivalent to dv du. Now this equation can be written as xy into p square plus 1 equal to x square plus y square minus 1 into p. That is the given equation. Look at the given equation. You can write this given equation, and xy, you can take xy common from these two terms and you can write this. So you can divide by p. It will be xy into p plus 1 by p, right, equal to x square plus y square minus 1 and p not equal to 0 in this case. So you once again, if you expand, so let me show you, open the bracket, it will be xy by p. Let me write once again the previous trick. How will you write? We have to write yp by x. We have to write yp by x. So in the first term, yp by x. So I have taken an extra x, so x square, and the denominator will be x by py into y square. It's a similar result. It's a similar result because it's a similar problem. H square is 1 in this case, so you can do the problem right now. Okay, so look at that. This is your q, this is once again q. So I'm showing you two problems once again. So q 1 by q, this will be 1 by q, right? So q u plus v by q equal to u plus v minus 1. And in this case, if you check, it will be v equal to uq plus q into q minus 1, q by q minus 1, q not equal to 1. So in this case, you have a same type of problem as the previous one. Just the difference is that you have h square, replacing h square by minus 1. That is the difference. But you have the same type of problem here. So I'm not going to discuss about this problem further. You can easily understand, and you can find a singular solution in this case also. So let me give you another problem. This is the last problem. Look at the substitution. Substitution is not of u equal to x square. It is substitution is given u equal to y and v equal to xy. This is given here. This is given here. So how will you do the problem? And the problem is x square p square plus yp 2x plus y plus y square equal to 0. So let me write y equal to u, v equal to xy. So your xy equal to v implies dv dx equal to xp plus y, because p is your dy dx, okay, and that is equal to xp plus u. Okay, now what is your dv du? dv du is given by, what is your dv du? dv du is given by dv dx by du dx. So your dv dx is xp plus u, and du dx is your p, because dy dx. So we can write this du by dv dx du dx, right? So this is your xp plus y by p, xp plus u by p. So this can be written as x plus u by p. Look at that. And what is your x? X is v by u. So this is your v by u plus u by p. Look at the transformation. Look at the transformation. So dv du is q. dv du. So this is again written as, you can write dv du as q, or dv du minus v by u equal to u by p, right? So that u dv du, this is the transformation actually, v in equal to u square by p. So this is the manipulation here. You can write dv du equal to q also. Q is equivalent to dv du. You can write that, and you can change your q into p. You can write this also. So let's go to the problem now. What was the problem? You can, if you open the bracket, you will see it is xp plus y whole square. So your given equation can be written as, the given equation can be written as xp plus y whole square plus y square p, right? Plus y square p equal to 0. So you look at that, your xp plus y is given by dv dx. Look at that, it is dv dx, it is given by dv dx. So you have a dv dx here, dv dx whole square plus y is your u square, and p is your, p can be written as p is your du dx. Look at that, p is your, you can write p as your du dx, or you can write, let me write once again, p square, you take a p here, you take a p, okay, let me write, okay, no problem. So you can write dv dx whole square, and y is your p, look at that, y is your u square, and p is your dp du dx equal to 0, and you can take another p here, so it can be written as dv dx whole square to make it a whole square du dx. So u square by p, because p is your du dx, so it is du dx whole square, it is du dx whole square, right? Because p, why p is your du dx, because u is your y. So look at that, du dx equal to dy dx, that is equal to p. That was the calculation. So I have taken an extra p here, so I am multiplying with du dx, so that is balanced. That is why I want to make it a square, and the right hand side will be 0. Now let me transform, let me take dv dx by du dx, this whole square equal to minus u square by p. Okay, now this is written as dv du, this is given by dv du whole square, plus what is your u square by p, u square by p you have calculated here, u square by p is u dv du minus v, u dv du, you can manipulate from here, u square by p, that is u dv du minus v. So it is your u dv du minus v. So let me write minus v equal to 0. So if you simplify and writing dv du equal to q, you will get v equal to uq plus q square. So that is the Clairaut's form in v and u and q, right? So let me add one page. Okay, it's gone to the first page. Okay, so that was your just wait for a few seconds. So v is equal to uq plus q square, that was the form actually. What you get here, v is equal to uq plus q square, that was I was talking about. So what is the general solution in this case? What is the general solution in this case? If you differentiate with respect to u, let me show you. So this is the Clairaut's form. The general solution is given by v is equal to uc plus c square. The general solution is v is equal to uc plus c square. This is the general solution, and v is your xy and u is your yc plus c square. So this is the general solution. This is the general solution of the complete primitive. Now what about the singular solution? For singular solution you have to differentiate this with respect to u. So v, let me write v is equal to uq plus q square. So that will be given by v dv du, right? You have to differentiate with respect to u. So that is equal to q plus u dq du plus 2q dq du. Okay, and you these terms are cancelled, this term dv du is q and this is q cancel, so you are remain u plus 2q into dq du equal to 0. So either you have dq du equal to 0. Already I have written the complete primitive. Like this, but I am showing you for the singular solution. Y q equal to constant c. So if you substitute, you will get the singular solution complete primitive. And the second thing is that you will get from here u equal to minus 2q. So if you substitute u equal to minus 2q in the given form, v is equal to uq plus q square, what you have, so v equal to u means minus 2q square plus q square, so that will be minus q square. So look at that, this will give you the singular solution. If you can eliminate q, yes, we can eliminate q from 1, that is from u equal to minus 2q, you can substitute your u. So v equal to minus u by 2, eliminating q. I am eliminating q between these two. So you look at that, you have no constant and you have no q in this final form, so that will be your u square plus 4v equal to 0. This is the singular solution. If you replace your uv with xy, then that will be y square plus 4xy equal to 0, and it will give you the finally y square into y plus 4x is the singular solution. This is the singular solution, So that was I was talking about. So in this lecture you have learned how to transform mainly the Clairaut's form, transform the ordinary differential equation of first order but not of higher degree, not of first degree, first order differential equation of higher degree transformed into the Clairaut's form with the different substitution. If the substitution is given in the problem, maybe the substitution is not given in the problem, but you have to transform, and how to get the singular solution with that transformation. So these problems are very, very important. Also the concept of some observations, important observations, and the geometrical interpretation of Clairaut's form. And Clairaut's form is actually invariable with the transformation. So these are the lecture today. So I'll stop here. Thank you all of you for your patience. We'll see in the next lecture.